Hey everyone, welcome back to the Bare Metal Embedded Systems Programming from Scratch series. In the previous episode, Registers and Addresses Part 1, we mapped the PMC registers, defined the oscillator and PLLA bit fields, and built the foundation needed to control the clock system of ATSM3X8E. Today is Part 2. In this episode, we'll continue exactly where we left off and explain PMC Status Register flags, Master Clock or MCK selection and prescaler, Flash Wait State registers, and PIO or GPIO register mapping for our LED. This is where our register definitions allow us to observe and synchronize with real hardware state. Let's get started. Let's begin with the Power Management Controller Status Register, or PMC_SR for short. This register is read only. We never write to it. We only read it to check when the hardware is ready. If you check the datasheet on page 555, you will find the complete description of all its bits. We'll start by defining the bit position and bit field for the first important bit, the main crystal oscillator status. And here we say hash define PMC_SR underscore MOS CX TS underscore POS 0U and hash define PMC_SR underscore MOS CX TS and inside parentheses 0x1U shifted by the position. This bit shows when the external crystal oscillator has started and stabilized, a crucial step before using it as a clock source. Next one is the PLLA lock status bit. Hash define PMC_SR underscore lock A underscore POS 1U. Hash define PMC_SR underscore lock A and inside parentheses 0x1U shifted by the position. This bit signals that PLLA or phase lock loop A has locked on the target frequency until it's set that PLL output is unstable. Then we define the master clock ready bit. Hash define PMC_SR underscore MCK RDY underscore POS 3U. Hash define PMC_SR underscore MCK RDY inside parentheses 0x1U shifted by the position. When this bit turns on, the master clock or MCK has finished switching and is stable. The CPU can now safely rely on the new clock source. Finally, the main oscillator selection status bit, hash define PMC_SR underscore MOS CS ELS underscore POS 16U. Hash define PMC_SR underscore MOS CS ELS and inside parentheses 0x1U shifted left by the position. This bit indicates whether the main oscillator clock source switch is in progress. Now we're diving into the master clock register or PMC_MCKR. This register is super important because it decides which clock drives the CPU. You can check all the details in the datasheet on page 550. PMC_MCKR is read-write, so we can safely configure it in our code. Let's start by defining the position for the first part of this register. Hash define PMC_MCKR underscore CSS underscore POS 0U. This is the start of the clock source selection or CSS bit field, which uses bits 0 and 1. Next, we define the mask for the CSS bit field. Hash define PMC underscore MCKR underscore CSS underscore MSK, and inside parentheses 0x3U shifted by the position. The mask helps us isolate these two bits without affecting any other bits in the register. This ensures we can safely update the clock source without accidentally changing other settings. And now we define the main underscore CLK option for the CSS bit field. Hash define PMC underscore MCKR underscore CSS underscore main underscore CLK, and inside parentheses 0x1U shifted by the position. This value selects the main oscillator as the clock source. By using this, we tell the hardware to run the CPU directly from the main clock. And here's the PLLA underscore CLK option for the CSS bit field. Hash define PMC underscore MCKR underscore CSS underscore PLLA underscore CLK, inside parentheses 0x2U shifted by the position. This value selects PLLA as the CPU clock source. Using this, the CPU will run from PLLA output, which allows us to use a higher frequency than the main oscillator. In the next episode, we'll put all these pieces together. You'll see exactly how to use these bit fields, and everything will click into place. That's when it all starts to make sense, and the clock system really comes alive. Now we move on to the master clock prescaler bit field. Hash define PMC underscore MCKR underscore PRES underscore POS for U. Hash define PMC underscore MCKR underscore PRES underscore MSK, and inside parentheses 0x7U shifted by the position. And hash define PMC underscore MCKR underscore PRES underscore CLK underscore 2 inside parentheses 0x1U shifted by the position. This bit field controls how much the selected clock is divided before it reaches the CPU. Setting this value selects a divide by 2 prescaler, which means the CPU runs at half of the selected clock frequency. This is important because it allows us to run the system safely within the CPU's maximum frequency limits. Next, we define the base addresses of the flash controllers. Hash define EFC0 underscore base 0x400 E0A00UL, and hash define EFC1 underscore base 0x400 E0C00UL. The AT73X8E has 2 embedded flash controllers, one for each flashbang. Both flashbangs can be accessed by the CPU, so each controller must be configured. That's why we define both EFC0 and EFC1, to make sure flash timing is correct no matter which bank the code is executing from. And then we define the flash mode register or FMR for each flash controller. Hash define EFC0 underscore FMR reg 32, and we pass in EFC0 underscore base plus 0x00U, and hash define EFC1 underscore FMR reg 32, and we pass in AFC1 underscore base plus 0x00U. The flash mode register controls how the flash memory is accessed. By mapping this register for both controllers, we can configure flash timing for each flash bank. You can find all the details about this register in the datasheet on pages 303 and 304. This configuration becomes especially important because when we switch the CPU to 84 MHz, the flash memory is much slower than the CPU. Without configuring this correctly, the CPU would try to fetch instructions faster than the flash can deliver them. That's why we must adjust the flash settings before running at higher frequencies. Now we define the flash wait state bit field. Hash define AFC underscore FMR underscore FWS underscore POS 8U. Hash define AFC underscore FMR underscore FWS, and it takes V inside parentheses UN32 underscore T V shifted by the position and 0xFU shifted by the position. Bits 8 to 11 of the flash mode register control the number of wait states for flash access. This macro lets us easily set the number of wait states in code. Since the CPU running at 84 MHz, we need to increase the wait states so the flash can keep up. Without these wait states, the CPU would try to fetch instructions faster than the flash can deliver them, which would cause errors. Now, it's time to define the parallel input-output controller B or PIOB base address. Hash define PIOB underscore base 0x400E1000UL. This is the starting point for all GPIO registers of port B. With this base, we can configure pins, set them as output, and control devices like LEDs directly from our code. And then we define the PIO enable register or PER for PIOB. Hash define PIOB underscore PER reg 32, and we pass in PIOB underscore base plus 0x00U. This register enables PIO control over the pins. Without setting a pin in PER, the PIO cannot control it. So this is the first step before configuring any pin direction or output. The next register we need is output enable register or EER for PIOB. Hash define PIOB underscore OER and reg 32, we pass in PIOB underscore base plus 0x10U. This register controls whether a pin works as an output or input. Only pins that are both enabled in PER and set in OER can be driven high or low by the PIO. If a pin is enabled in PER but not in OER, it'll still act as an input, so we cannot write to it yet. Now we define the set output data register or SODR for PIOB. Hash define PIOB underscore SODR reg 32, and we pass in PIOB underscore base plus 0x30U. Writing a 1 to a pin in this register sets the pin high. Only pins that are enabled in PER and set as outputs in OER can be controlled here. This register is write only, so we don't read it. We just use it to turn pins on. And finally, we define the clear output data register or CODR for PIOB, hash define PIOB underscore CODR reg 32, and we pass in PIOB underscore base plus 0x34U. Writing a 1 to a pin in this register sets the pin low. Just like SODR, only pins enabled in PER and configured as outputs in OER can be controlled. CODR is write only, so we use it purely to turn pins off. And next, we define the peripheral ID for PIOB, hash define ID underscore PIOB 12U. This ID is used to enable the clock for PIOB in the power management controller. You can find this ID on page 38 of the datasheet. Without enabling the peripheral clock, the PIO won't work, even if all the registers are configured correctly. Now we define the LED pin number, hash define LED underscore pin 27U. This is the specific pin on PIOB that our LED is connected to, PB27. Finally, we define the LED mask, hash define LED underscore mask, and inside parentheses 1U shifted by LED underscore pin. This creates a bit mask for our LED pin, making it easy to set, clear, or toggle the LED in a single operation. And that's a wrap for Register and Addresses Part 2. Today, we mapped out the PMC Status Register and its key bits, how the master clock is selected and prescaled, why flash wait states are crucial at higher CPU speeds, and the PIOB register to control our pins, including the LED. In the next episode, we'll bring it all together by defining the clock init function. You'll see exactly how to initialize the oscillator, PLLA, and switch the CPU clock to 84 MHz. If this helped you understand the inner workings of the AT73X8E, hit like, subscribe, and leave your questions below. Thanks for watching, and I'll see you in the next one.